Hello again. We're going to be graphing polynomial graphs. Graphing polynomials is probably the way I should phrase it. And we're going to use a couple of techniques. One is through factoring, the other is through factor theorem. And there's actually a multitude of different ways that you can graph polynomials. Some of them don't work out as easy as others. I prefer other methods, and I'll show you later. But this is a way to graph something that's going to work. They're not going to give you a problem in a book, using a factor theorem problem that doesn't work, and they're not going to say factor this and it's not going to not work. The problems are prescribed the way they are. So it's going to be kind of like this too. Now, these are a couple of different approaches, and the best way to actually graph any sort of polynomial, whether or not you actually like it, if you want the most accurate representation, and then you can use Newton's law of zeros. Well, it's not called the law of zeros. I forgot what it's called. It's called in calculus, but that doesn't even really work completely as well. So the best way to really do it is through tables. And a lot of people don't want to write tables. I don't blame you. I probably wouldn't want to write a table of this either. I'd probably just plug this in my graphing calculator, which seems to be a cardinal sin, but it is something that I'd probably do for these two, for different problems. Not these particular ones because they work out nicely. So I want to graph this, or I want some sort of estimation of a graph. And I've got x to the fourth minus 13x squared plus 36 equals 0. Now, one way you can do it if the problem allows it is through factoring. And I can factor this. I can factor this into, well, it's a little bit of a jump. What times what is a negative, but adds, I'm sorry, positive, but adds up to be a negative? It'd be a negative and a negative. X squared times x squared will be x to the fourth. And what times what is 36 but adds up to be negative 13? It's 9 and 4. If you don't believe me, go ahead and FOIL this out and check it. It really does work. And it's all equal to 0. And now what I'm going to do is I'm going to factor each one of these binomials because they're both perfect squares. This is x plus 3x minus 3. And x squared minus 4 is the same thing as x plus 2x minus 2. You just got your roots. Negative 3, 3, negative 2, and 2. And that's actually something that my teacher had shown me when I was very young, when I was first doing this mathematics. And I said, well, doesn't the graph have to be perfect? And she says, no, it doesn't. It's just your understanding has to be clear. You don't have to draw everything perfectly. It just, what you convey has to be right, though. So if I do that, see if we can understand this. The roots are at negative 3 and 3. The zeros, the real zeros, or real roots, pardon me. And they're at negative 2 and positive 2. Okay. It's a fourth degree polynomial, and it's positive, which means if it's positive, the right arrow is going to go up. But it's fourth degree, which means it's even as well, which means both arrows are going to go up. Now, this isn't a perfect graph. I should preface that. But, what is going to be perfect? And there you go. Something like that. It looks like a W. It's not going to be perfect. If you go ahead and graph this, it might not look exactly like this. And that's not the point. What I'm giving you is a rough estimation of what it can look like in your head without enabling you yourself to use a graphing calculator. And in this particular problem, you shouldn't have to use a graphing calculator, which is pretty cool. So I'm going to erase this one and go on to the next one. And we're going to use something called the factor theorem. It's another method. It's not my favorite method, but if you employ a series of methods, tools to do this, that's fine. There's another method I'll show you later. Well, not later, not much later, but later. So let me go ahead and erase this one. And basically what you were able to do with that was find the zeros, the real zeros. There were no repeating roots, and there were 4 real roots. Okay, with this one, you want to graph x cubed plus 6x squared minus x minus 30. And you're given the information that x plus 3 is a factor, that it will actually work. So what I'm saying is like x plus 3 in a quantity times some other stuff equals 0 will end up working. Well, in order to do that, you can use a couple of different methods. You can use something called synthetic substitution. You can use synthetic division. I prefer synthetic division because I know I've shown that already. And how you do synthetic division is pretty easy. You take the opposite of this number, which is negative 3, And you take each coefficient of this graph, 1, 6, -1, and 30. And you go ahead and do this in synthetic division. This drops to be a 1. -3 times 1 is -3. 6 plus -3 is 3. -3 times 3 is -9. -1 plus -9 is -10. -3 times -10 is 30. The remainder is 0. But of course that's going to be the case because I told you that that's going to be a factor. So pretty interesting there. There's a reason why this works very nicely. What it does is it depresses the polynomial function. It doesn't make it sad, it just depresses it. It brings it down a degree. So this was x cubed, now it becomes x squared plus 3x, subtract 10, and then you got remainder 0. That's really cool actually, because you can factor x squared plus 3x minus 10. Into two binomials. Positive and negative will work. X and x. What times what will be 10 but add up to be positive 3, pardon me. It's going to be 5 and 3. But I already know that x plus 3 is also a factor. You can check it out for yourself. Multiply this one by this one by this one, and you'll get x cubed plus 6x squared minus x minus 30. It's really cool. And, well, you know, that's what p of x equals. But let's say I want, you know, some sort of graph. All I did was I rewrote this to look like this. But the reason why I did that is because now I can locate my zeros. And they're at -3, -5, and positive 3. Let me just make sure I got that right. -3 I got, -5 I got, and 3 I got. Perfect. And it's a positive function, which means the right arrow is going to go up. It's positive because the number in front of the leading coefficient, or the number in front of the variable with the highest degree, is positive. And it's an odd function, which means one arrow goes up and one arrow goes down. So, ignore that. It'll look, that's pretty bad, but it'll look something like that. It'll cross here, here, and here. It's got 3 real roots, no imaginary. One arrow, well, right arrow goes up, you know, odd function. Pretty cool. Actually, I think it's probably more like this. I just drew that poorly. But, yeah, I mean, you were able to draw a function without the use of a graphing calculator. That's what's so cool about it, and that's what people have been doing for, you know, hundreds of years, maybe thousands of years when it came to these things. It's just a different way to think about it. With that said, I hope that was helpful in terms of graphing polynomials. You don't need to graph polynomial graphs. Have a nice day. Goodbye.